These last two examples bring us to the point where we are putting everything together. We're going to have to look at the series rules that we came up with earlier. We're going to have to look at the parallel rules and then put them all together, keeping them straight where we need to use them. So we're supposed to calculate some things. We're supposed to solve this circuit. We are given the total current, which is 3 amps in case that's not clear. We're given the resistance of resistor 1, 2 ohms. This one's 3 ohms. This one's 2 ohms. And what we are supposed to find is the equivalent resistance and all these other things. Okay? So in the last video, we showed how to find equivalent resistance for a combination circuit. You just have to be careful about where you start. So I see that R3 over here is in parallel with R2 because they are not part of the same path. They are in two different paths. However, R1 is part of the R2 path and it's part of the R3 path. And so R1 is in series with R2 and it's in series with R3. So the first thing that I will need to do is combine R3 and R2 in parallel before I can bundle in R1. Okay? So R2 plus R3, I'm going to call that R4. Let's just use green for that. So these two are going to be R4. And R4 is parallel, and so we're going to have to use the reciprocal rule. 1 over R4 equals 1 over R2 plus 1 over R3. And so that gives us 1 over R4 is equal to 1 over 3 plus 1 over 2. And when you put those together, you get 2/6 and 3/6, which is 5/6. Flip it upside down, and you get 6 over 5. That's the resistance of this combination here together. Now, if we've done it right, this should be smaller than either of these two resistances. And it is, so that checks that box. So now, when we want to figure out the equivalent resistance, all we've got left is this R1 that is now in series with this single combined resistor that we've made. I'm not going to redraw this for the sake of space. But now, when I'm figuring out the equivalent resistance, then what I need to do is just combine in series R1 and R4. Okay, they are now in series with one another. So the equivalent resistance equals R1 plus R4. They're in series, so we just combine them just like that, and you get 2 ohms plus 6/5, which is 3 1/5. Or if you prefer, 3.2 ohms. And that is what I'm going to use just for the sake of consistency with decimals. Okay, so this is 3.2 ohms. That's the equivalent resistance of this entire circuit. Now we're going to move on to the voltage. Now, this particular question basically gives you the order that you need to solve it in, but they won't all do that. You will need to be able to figure out yourself, what do I find first? Now what can I find next? So the sequence of filling in all the blanks, that's going to be up to you in the end. This one is just meant to walk you through it. So now I have the equivalent resistance, I have the total current, which means I can find the total voltage using V equals IR for the whole circuit. So VT equals IT times RT, or REQ, same thing. VT is equal to 3 amps times 3.2 ohms. And so VT, the total voltage in the circuit, is 9.6 ohms. Not ohms, volts. 9.6 volts. So we've got VT. Now we're looking for the current through resistor 1. That's I1. Now, this resistor is connected in series with the source. And so if we draw our path diagrams here, just really quickly, there's one path, and I'll use purple for the other path. No matter which path an electron goes down, it has to pass through this resistor. That means that all current is going through this resistor. So I1 is going to be equal to I total. Okay, so I1 is equal to the total current, which is 3 amps. Okay, so we know that 3 amps is running through this resistor. Now at that point, we can also figure out the voltage drop for that resistor, because when you have two pieces of information, you can use Ohm's law, V equals IR, to figure out the third piece. And so we're going to move right over here. V1 is equal to I1 times R1. V1 is equal to 3 amps times 2 ohms, and that is equal to 6 volts. So there's a 6 volt drop in R1, and that means that of the total 9.6 volts, only 3.6 is left in these two resistors. Okay, now this is important. When we talked about the voltage in parallel branches, we said that in each path, all the voltage has to drop, right? Now R1 is in both paths, and so part of the voltage is going to drop across this resistor, and if we're looking at the red path, the rest of the voltage has to drop across this resistor. So if 6 volts dropped here, that means 3.6 has to drop here, because in the red path, all of the voltage has to drop. And so that means V2 and V3 are both going to be that remaining 3.6 volts, because 3.6 volts has to drop here, and in the purple path, 3.6 volts is left to drop here. And so V2 and V2 equals V3, which equals 3.6 volts. Now, I2. Now that we know the resistance of this resistor, and we know the voltage drop, we can figure out the remaining current that's going through this branch using V equals IR. So V2 equals I2R2. And we know that V2 is 3.6 volts. I2 is what we're looking for. And R2 is 3 ohms. Okay, and when we divide that, we get I2 is equal to 1.2 amps. Now to find I3, we have a couple different options. So option 1, we know R3, the resistance, and we know V3, the voltage drop. So we can just do Ohm's law again, V equals IR, and figure out what the current is through here. Option number 2, we know that the entire current is 3 amps. So 3 amps travels through this resistor, and then it splits at this junction. Okay, and we know that 1.2 amps goes through this branch, and the remaining current has to go through the other branch. So if we have 3 amps altogether, and this is 1.2, then this must be 1.8 amps. I3 is equal to I total minus I2. And so I3 turns out is 1.8 amps. And we've solved for everything. And this is our final skill, being able to solve for all the unknowns in a given combination circuit. So we first have to take stock of what we are told, and then we can figure out what piece can I fill in first, or maybe there's multiple pieces. There's probably multiple orders that this can go in. There's not one set way that you have to discover to make it all the way through. You're just going to have to use the tools that you have for solving circuits, Ohm's law, Kirchhoff's laws, things like that, and then figure out what order can I actually do it in. So, first of all, we are told the equivalent resistance for the circuit is 5.122 ohms, in case you can't read that. The total voltage increase at the source is 8.195 volts, and the total current we aren't told, but because we have both of those pieces, we can use Ohm's law to figure out the total current. Then we're told that this resistor up here is 5 ohms, this one's 3. We're told nothing about this resistor. This one we're told is 2 ohms, and we're given the voltage drop for this one, so we can fill in that current right away using V equals IR. And then this one we are told the resistance as well. So I'm just going to go through this thing and try and fill in as many pieces as I can that make sense to me. So first of all, I'm going to solve for total current first. V T equals IT times RT. And I'm solving for current, so my current is going to be the voltage divided by the resistance. So that's 8.195 volts divided by 5.122 ohms. Now I'm going to work everything to 3 decimal places. So when we do that, we get 1.600 amps. That's our total current. 1.600 amps. Okay, so we have that current. Now I'm also going to fill in I3 over here because I see that that's another piece that I can get using V equals IR. So V3 equals I3 times R3. And I'm solving for that current again, so I3 is equal to 2.133 volts divided by 2 ohms. And that gives me 1.067. 1.067 amps. That's I3. Okay. Now, some other things that I know because I know about circuits. This resistor right here at some point is going to have all the current running through it. No matter which path you take, now we can draw several paths here, so I'm not going to draw them out in this case. It'll get too ugly. But I know that every single path will take its current through this resistor. And so I know that the current through this resistor is going to be 1.6 amps. There is no other way for current to get back to the source than to go through this resistor. Okay. I also know that my current going through this resistor is 1.067 amps. And this 1.6 amps, once it reaches this junction over here, is going to split and go down the R3 path and go down the R4 path. And those are the only two choices once it gets to this junction. And so my 1.067 amps is going to take up part of my 1.6 amps current. The rest is going to be I4. And so figuring out I4, it turns out, is not a big deal if I remember that junction rule. So I4 is going to be equal to the total current, IT, minus I3. And that's 1.6 minus 1.067, which gives me 0.533 amps. That is I4. Now I see that I've filled in 2 parts of a 3-part component here, so I can use V equals IR to figure out what V4 is. So V4 is equal to I times R, so that's 0.533 amps times 4 ohms, and that is equal to 2.133 volts. 2.133 volts. Now you may notice that that is the same as V3, and so it should be. We said that in every path the total voltage has to drop for each of them, right? And so in this parallel branch we've got 2.133 volts dropping. Well, in the other one it's got to be the same. Okay, so we know that in parallel branches they have the same voltage drop. So that should have been expected. We could have filled that in before. Now we've got this last bit over here, and this is the tricky part. I see that I could combine these 2 resistors here because they are in parallel with each other. So that would make one series component with the rest of the circuit. I could do that. I could also combine these 2 resistors in parallel, and that would give me a much simpler circuit. That would give me a series resistor with a series resistor with a series resistor. And since I already know the equivalent resistance of the whole circuit, I could subtract these 2 resistances to figure out this final one over here. And then I think I'm off to the races, because then I would have two parts and I could figure out V5 over here as well. So I'm going to do that. You may be able to find out another way of filling something else in, but that's the road that I'm going to take. So I'm going to call this parallel complex over here, I'm going to call this R6. And this one over here, I'm going to call R7. So, because R6 is being calculated in parallel, 1 over R6 is equal to 1 over R1 plus 1 over R2. And so R6 is going to be 1 over 5 plus 1 over 3. Okay, and when I flip that upside down, I should get 15 over 8. Okay, so if when I add this together I get 8 over 15, 15 over 8 is R6. But since I'm doing everything to 3 decimal places, I'm going to convert that to a decimal with 3 decimal places. That's 1.875. Okay, so that's R6. Then I want to do R7. 1 over R7 is going to be working the same way. So that's 1 over 2 plus 1 over 4. And so R7 is equal to 4/3, which is 1.333 ohms. Okay, so now I have this component over here. I've just exchanged it for 1 resistor. This part over here I've exchanged for 1 resistor. And so now to figure out R5, I can take REQ and I can subtract R6 and R7. So R5 then is equal to 5.122 minus 1.875 minus 1.333. And so my resistor 5 is equal to 1.914 ohms. Okay, so now I'm going to figure out V5, which is 1.6 amps times 1.914 ohms. And so the voltage drop for 5 is equal to 3.062 volts. And we'll put that in here as well. Now, I have filled in this voltage drop and these two. And so this being a series component, so these are in parallel with each other, but together this whole thing, R6 you could call it, is in series with the rest of the circuit, right? All electricity is going to have to pass through one of these two branches. And so we can figure out the voltage drop using the other voltage drops. So if we look at one path, and now I'm going to actually draw in one path. And let's just say it's going up the top. Doesn't really matter. Okay, that's one path. All the voltage has to drop in that one path. And so we've got a drop of 3.062, we've got a drop of 2.133, and we've got some unknown drop, but we know the total is 8.195. And so I'm going to figure out what V1 is based on subtracting the two voltage drops I know from the total. So V1 is going to be equal to 8.195 volts minus 3.062 and minus 2.133. And so V1 is equal to 3 volts on the nose, or 3.000 if you want to stick to the 3 decimal places thing. So this is 3 volts. I'm not going to write the decimal places in there because I can't fit them. And because these two components are parallel, that means V2 also has to be 3 volts. And then I just have to use V equals IR to figure out the missing currents. And so when I do that, I get 0.6 amps. And 3 divided by 3 is 1 amp. And those two, 1 and 0.6, should add up to the total. And they do.